beginning our last unit, which is a permutations, combinations, and the binomial theorem. We'll look at Pascal's triangle along the way. Basically, it is a unit on probability and counting principles, which is generally useful all throughout university. It pops up in a lot of different places. It's actually very tricky stuff. We don't take a very deep dive. We used to take a deeper dive into this about 10 years ago, but the curriculum changed, so this is what we do now. Anyhow, let's go ahead and take a peek at what we're dealing with here. So, what is this thing called the fundamental counting principle? Well, basically it boils down to this. How many different ways can you know that an event can happen? This is actually a really complicated area of mathematics that we call probability. We're going to take, like I said, a shallow dive. Mama used to say stay away from the shallow ones, but here we go. So what is the fundamental counting principle? Well, it states that if there are an m number of ways for an event to occur, and an n number of ways of another event occurring, then the total number of ways that both events can occur in conjunction is m times n. And that's the fundamental counting principle. It sounds pretty simple. So just to illustrate like what it might look like in real life, say you're a carpenter and you either use oak or pine wood, and then you offer 3 different colors of wood stain, light, medium, and dark. How many unique tables can the carpenter make? Well, so basically what we're going to do is we're going to build some stuff, right? And from there you can say, well, we can build it out of oak or we can build it out of pine. Now, if we choose oak, there are 3 options for the color. We can do a light, a medium, or a dark. So I can build an oak light table. So oak light, I can build an oak medium, and I can build an oak dark. So there's 3 different sort of oak tables. Same thing with pine. I can go light, medium, dark. So you guys are getting the picture. We can go pine light, pine medium, sounds delicious, and pine dark. So how many ways, how many unique tables can we build? Well, there's 6 ways we can do this. So you can draw this out, and by the way, this is called a sample space. So a sample space is when you literally map out every single possible thing that can happen in a situation. This is called doing it by brute force, right? Like brute force, I literally figured out every single thing that can happen, so I thought about it. Well, if you're really clever, you would just use the fundamental counting principle, which says, hey, there's 2 different kinds of wood, and there's 3 different options that I can color them with. 2 times 3 is 6, so there's 6 unique things I can do. That's how you would use the fundamental counting principle to do this problem. What's easier when you get it is obviously this way instead of doing it by brute force. So I got a little note down here about the sample space. Sometimes on the exam, they might actually ask you to draw out the sample space. So obviously they stick to problems that aren't like ginormous or gymongous, as my kid would say. All right, let's look at another example of the fundamental counting principle in action. So like I said, when you list all the possible outcomes, that's called a sample space. Let's say, no, this is basically me. So Demuro. You know, I got 4 pairs of pants, 3 sweaters, 5 pairs of shoes. How many different outfits can I make? Well, I don't want to do the sample space because this is going to start being sort of a lot of work. But I know from the fundamental counting principle that if I just multiply all the different ways that things can happen together, then I'll get the unique combination. So I can just say, all right, I got 4 pairs of pants times the 3 sweaters times the 5 pairs of shoes. Let's see, that's going to be 15 times 4 or 60 outfits. Okay, so to be a unique outfit, only one thing needs to be different. So that's way easier than doing the sample space. The sample space would have had 60 different things in it. It's a lot of work. On the exam, they like to use numbers. So they'll ask you questions like this. So you might they might say, okay, you're going to use the numbers 1 to 7 inclusive. So I listed them out here. And then they might ask something like, well, how many 3-digit numbers can you make if you're not allowed to repeat any digits? Okay, so once I use a 1, I'm not allowed to use a 1 anymore. So when I do these ones, I like to sort of draw some spaces for my numbers. Now they're 3 digits. When you choose your first digit, how many options do you have? Well, there's 1, 2, 3, 4, 5, 6, 7. There's 7 options. Now I'm going to multiply because the fundamental counting principle says you multiply the number of ways things can happen together. So if I'm not allowed to repeat, I've used 1 digit here. Okay, so now I only have 6 left for the next digit and then 5 left for the last one. When I multiply them together, I'm going to get 7 times 6 times 5, which is 210 unique 3-digit numbers. Okay, so I like to do it this way, just in case it's not clear. This is the second digit, and this is the third digit. So sometimes there's some confusion. People think like I mean this is going to be a 7. I just mean I got 7 ways or 7 options, then I have 6 options, then I have 5. Let's move on to the next one. So it's the same as part A, but now we can repeat digits. Well, if we can repeat digits, here's my 3-digit number. My first digit, I have 7 options. For my second digit, well, I still have 7 options, but I'm allowed to repeat numbers. And then for my third digit, I have 7 options. So 7 times 7 times 7 is 343 ways. All right. What about part C? Well, how many 3-digit numbers can we make if we cannot repeat the digits and they must be even? Okay, it's starting to get a little bit tricky. So draw out your 3 spaces. They have to be even. What makes a number even? Well, it would have to end with a 0, a 2, a 4, a 6, or an 8. Those are the options. I'm using the numbers 1 to 7. So I have a 2, I have a 4, I have a 6. Okay, so for this to be an even number, I'm actually going to do this part first because there's only 3 options I can use here. Okay, now none of the other digits matter to make it even. It's just the end digit that makes it even. So I cannot repeat digits. So I've used 1 here, right? I've used 1 digit. So how many do I have left? I started with 7, I used 1. So for this digit, there's 6 options, and I can't repeat. So for this digit, there's 5, right? Because we're multiplying, it doesn't matter the order we multiply in, right? So 6 times 5 times 3, we are going to get, what is that? Is that 90? 90. There's going to be 90 ways. These seem really simple when I explain them, but I really recommend that maybe even after I finish up this slide, that you pause the video and try doing these again without looking. You'll be surprised because it's not quite so easy. You really have to think. That's what makes this unit tricky. So part D, same as part A. So basically, we're using 3-digit numbers with the numbers 1 to 7 and no repetition. But now we're making odd numbers. Right. So I think this might be worded a bit strange. Not using odd numbers, but making odd numbers only. So here's my 3-digit number. What makes a number odd? Well, it would have to end in a 1, a 3, a 5, or a 7. Or a 9, but we don't have 9 available, so we have 1, 3, 5, 7. So there are basically 4 options here that I can use, and I have 7 numbers in total, and I can't repeat. So that means I have 6 left for this digit, and I have 5 left for this digit. When you multiply this together, give you a moment, you get 120 ways. Neato. Part E, same as part A, but the numbers must be greater than 300. Well. This is like expert mode. Oh no, sorry. I clicked my button. There's my 3 numbers. That's just a scribble. It's a bicycle. There. That does not look like a bicycle. So, greater than 300. Well, what would make a number greater than 300? Well, first of all, this would have to be a 3. Okay, now we're using the numbers 1 to 7, so I'm just going to write them out here just so I can look at them. Now, if it's greater than 300, I would not be able to have the number 300 exactly. The good news is that can never happen if I'm using these numbers. I don't have 2 zeros to use. I don't have any zeros to use. So basically, when I'm thinking about this, the only condition is this must be a 3 or higher. Okay, so how many numbers do I have that are higher than 3 or equal to 3? So 1, 2, 3, 4, 5. So I got 5 options here. Now again, there's no repetition, so I have 5 options for this number. I had 7 to pick from. I've used the number, so that means there's 6 left. Okay, and then for the last digit, there's 5 numbers left. So when you go 5 times 5, which is 25, times 6, that's 150. All right, last one. Same as part A. So using the numbers 1 to 7, no repetition. The numbers have to be less than 300. Ooh. what makes a number less than 300? Well, let's think. If I have a 3 here, it's not going to be less than 300. Now remember, you only have these numbers to use one time each. Okay, so for it to be less than 300, this has to be a 1 or a 2. So there's only 2 options here. And then, same logic as before. I had 7 numbers, I've used 1, there's 6 left, and then there's 5 left. So 2 times 6 is 12, times 5 is 60 ways. Okay, so obviously the easiest way to do these questions is using the fundamental counting principle. But theoretically, for every question, you could write out every single possible example and get the sample space and count that up. That is not recommended. Computers are good at doing that. You could write code that could do it for you, but if you're just doing it as a human, you don't have that option. So I recommend you pause this and then try it again. So moving along, we're going to introduce a new thing called a factorial. So basically, in probability, you're often going to find yourself multiplying down from a number until you get to 1. Okay, I haven't gone to those questions yet, but it's going to start happening soon. So there's a useful mathematical device called a factorial, and we actually use an exclamation mark to denote a factorial, which when we place it after a number, it means you're going to start on that number, and you're going to multiply down from that number until you get to 1. Okay, so always subtracting 1, you're going to do that. Here it is. Here's a factorial. 4 factorial. How do you write it? Well, 4 factorial means, and by the way, it doesn't mean 4, it means 4 factorial, so that's how you read it. It means you go 4, and then you subtract 1, and you multiply that number, and then you subtract 1, and you multiply that number, and then you subtract 1, and you multiply that number. You are done multiplying when you get to the number 1. So that's what a factorial is. So you got 4 times 3 times 2 times 1. That's 24. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Now check this out. This is 4 factorial, so I know this is 24. So if you're looking for a shortcut, you can go 24 times 5 times 6 times 7 on your calculator. Give you a moment. That was exactly 1 moment. You get 5,040. And my kid's going to burst in here right now. Hey, buddy! Oh, you want this? Can I finish what n?
Are you drawing something?
Yes, I'm doing n factorial. Do you want to do it with me? So I'm going to start with n. And now, because you're doing it with a variable now, you're going to go n minus 1. And then for the third digit, it's going to be n minus 2, because it's n minus 1 again, so n minus 2, and then n minus 3. And because you don't know when you're going to get to 1, you just go ... 1. So this is setting us up for when we do it with variables. Okay? I got to pause for a moment here.
Why?
Okay, simplifying factorials. So you're going to work with some problems that may or may not look like this. It's going to be on the non-calculator part of the exam, if it comes up usually. So there are a couple factorials I recommend you know by heart. Now, 0 factorial is actually 0, and there is a reason for that, but we're not going to go over it. 1 factorial is 1, right? Because just 1 times nothing, I guess, is just 1, right? And then 2 factorial, that would be 2 times 1, so that's 2. So remember, 0 factorial 0, 1 factorial 1, 2 factorial 2. Once you get to 3 factorial, you got 3 times 2 times 1, so that's 6. And then 4 factorial we just saw, right? That's 24. 5 factorial is 120. If you really want to go pro mode, I do recommend that you do 6 factorial is 720. If you just have those memorized, it's going to make your life a lot easier. Okay, so questions like this, well, we can use algebra to solve. So, got to be a little sneaky. Obviously, they will use factorials that you might not be able to calculate without a calculator. So like 8 factorial divided by 6 factorial times 2 factorial. Well, there's a trick to this. Because we know that 8 factorial really just means 8 times 7 times 6 times 5. So we're just going to leave it right there. So write it as 6 factorial, right? I expanded it that far for a reason because I got a 6 factorial down in the bottom, right? And then a 2 factorial, which just evaluates to 2, so we can do that. So now, because I expanded the top so cleverly and I stopped at 6 factorial, I know that I got 6 times 5 times 4 times 3 times 2 times 1 in the top. I got the same thing in the bottom, right? Just represented by 6 factorial. So those will cancel out to 1, and you're just left with 8 times 7 divided by 2. Right now, 8 divided by 2 is 4, so you just got 4 times 7. So overall, this thing evaluates to 28. take a look at something like this one here. So again, same sort of trick. So I see a 5 factorial and a 7 factorial. So basically my advice to you would be expand the biggest factorial you have until you get to one that you can cancel. Okay, so my mission is I want to cancel this 5 factorial. So I'm going to expand the 7 factorial and write 7 times 6 times 5, and then I'm going to rewrite the factorial sign because I want to stop there, because I know that 5 factorial divided by 5 factorial is 1. Now 3 factorial I know is 6, so I have 6 over 7 times 6. 6 divided by 6 is 1, so you get 1 over 7. And that is about as easy as it's going to get. Now, generally on the exam, you're going to get questions that usually look like this. So on the non-calculator part, they might just say simplify this expression, and it's going to have variables in it. So I showed you how to expand n factorial, and n is just like a number, right? We just don't know what the number is. So we just know that every next number that we multiply, you subtract 1 from. Okay, so in an example like this, I recommend you start with the bigger number. So expand the bigger number. Which one's the bigger number? Well, n plus 3 or n plus 1? N plus 3 is obviously bigger, so we're going to start expanding it. So I'm going to write n plus 3 times n plus 2, right? Just subtracting 1 every time. That's what factorial means. And then after n plus 2, I'm going to have n plus 1. And I'm going to stop there. So I'm going to recopy the factorial sign. Why am I stopping there? Because look, in the denominator, I have n plus 1 factorial. So you're never going to be able to simplify this unless you can cancel out the factorials. So I got n plus 1 factorial, which is just a number, divided by n plus 1 factorial. So that's also just a number that divides out to 1. And now you're left with n plus 3 times n plus 2. Do they expect you to expand it out? I can't remember. I do believe so. To simplify completely, I'm going to FOIL it out. So that's just n squared, and then you're going to get a 5n, and then plus 6. Remember when that used to be hard in like grade 10? All right, so what if you have a question like this? Well, my advice to start with the biggest number holds true all the time because De Niro is just a baller like that. So when I say start, I should really say expand the biggest number. So here we go. N minus 1 is obviously smaller than n plus 2. So in the numerator, I'm going to keep my n minus 1. And I'm going to expand my n plus 2 factorial until I get to n minus 1. So I'm going to get n plus 2. Then I'm going to get n plus 1. And then when I subtract 1, I just get n. And then I subtract 1, so I get n minus 1. I'm going to stop, recopy the factorial. This divided by that is 1. So you're left with 1 over n plus 2, n plus 1 times n. Again, you'll have to read the question if they want you to expand it out. This is theoretically an answer. However, I'm going to expand it out. So first I'm going to FOIL that out. So that's going to give me n squared plus 3n plus 2, and it's still times n. Distribute the n into the brackets, and you'll get n to the power of 3 plus 3n squared plus 2n. And you're done, and you're oh so happy. And we are over halfway done our notes. So a bunch of reading on this slide. You may want to pause and highlight, but basically, the fundamental counting principle can be used in questions that take more than one step. These are often questions that involve the word or, and we usually call them case questions. So to find the total number of arrangements, you can basically find the answer for each one of the cases, and then you just add them up at the end. That just makes sense. However, it's important enough that we call it the addition principle of the fundamental counting principle. So just a small addition. All right, let's look at an example. So we saw questions like this that were shorter. This one's obviously a lot longer, and yes, these do show up on the exam. They're generally 2 or 3 mark questions. You'll get 1 if you get one. How many numbers are less than 300 if there's no repeats allowed? And now this is sort of me just commenting. So the question is, how many numbers are less than 300 if no repeats are allowed? So the problem here is that there's no demand for the numbers that only have 3 digits, right? So it just says numbers that are less than 300. So that could be 1-digit numbers, 2-digit numbers, or 3-digit numbers. So we have 3 cases, okay? So I'd say, I don't know, maybe start with the easiest the easiest case, right? So the easiest case in my mind would be maybe doing my 1-digit numbers. And I'm just going to write case 1. Okay, and then some of you might be like, well, what digits are we allowed to use? Well, the regular digits 0 to 9, right? So there's actually 10 digits, right? 0 to 9 involves 10 digits. You can count them up on your fingers if you don't believe me. So for a 1-digit number, I'm going to have 10 options. That's it, right? It could be 0, 1, 2, 3, 4, etc. The 2-digit numbers. 2-digit numbers. Well, that's case 2. It's a little bit trickier, right? So here's my 2-digit number. Now, for the first digit, let's think here very carefully. Can it be a 0? Right? So if you had 0, 1, is that a 2-digit number? And the answer is kind of like, no, like we would just say, well, that's the number 1. So the condition here, it's 1 to 9. Right? It has to be the numbers 1 to 9. So there's only 9 options there. Okay? No repetition allowed. You had 10 digits. You used one of them here, so now there's still 9 left. So there's 9 times 9, or 81 ways to get a 2-digit number. I'm going to put boxes around these answers because we're going to add them up at the end. And then finally, the 3-digit numbers. This would be case 3. Well, here's my 3-digit number. Just says they have to be less than 300, so we need to think very carefully here. So if it's less than 300, I clearly can't have a 4 here, or a 5, or a 6, or a 7. So I like to write underneath my little line here is like, so okay, what can I have? Well, I could have a 1 or a 2. I can't even use a 3, right? If I had a 3 here, and any number here, it could even be a 0, but my last number here would make it over 300, right? So I only have 2 options here. For the next digit, again, I had 10 digits, I used 1, so now there's 9 left. And then I had 9 digits, I used 1, there's 8 left. So 9 times 8 times 2, oh, that's easy to do in your head, it's 144. Just kidding. I mean, I'm not kidding, it is 144. Okay, actually that should be easy to do in your head. Anyways, so addition principle of the fundamental accounting principle says you can add these all up to get your answer. So just add them up. 10 plus 81 plus 144. There's 235 ways to do the thing they asked us. So it's about as hard as they get, I believe, on the exam. Some more case questions, of course. Let's take a look here. So we got how many 3-digit numbers less than 460 can be made from the digits 0 to 9 with no repetitions. Now, they'll generally specify whether or not you can use repetitions, by the way. So numbers that are less than 460, that's such a specific number. So there's probably going to be cases involved in here. And if you're just thinking, so like, this is what makes these questions hard, right? Like, oh god, here's my 3-digit number. If I start putting a 4 here, it starts getting tricky because I got to start worrying about what this number is. So you know what? Let's do the easy case first. What would the easy case be? Well, the easy case would be like, well, what if this was a 1, 2, or 3, right? There's no debate that if the hundreds digit is a 1, 2, or 3, obviously it can't be a 0 because it has to be a 3-digit number. There's no debate that this number will be less than 460. So that's my easy case. So 1, 2, or 3. So there's 3 options here. And then it doesn't matter what this is. So you have 10 digits. You used 1. There's 9 left. Use another one. There's 8 left. So now 3 times 9 times 8 is 216 ways. Now what about the hard case? Well, the hard case is going to involve having a 4 here, right? Now, because it has to be less than 460, this can't be a 5, it can't be a 6 or 7 or 8 or 9, and it can't be a 1, 2, or 3 because we already did those. So there's only one number that can go there, being a 4. Okay, now for this number, what can this number be? It has to be less than 460, so it could be a 0. It could be a 1, it could be a 2, it could be a 3. We don't have 4 anymore because we used it already, so it could be a 5. Now, if you put a 6 here, what's going to happen? The number's not going to be less than 460 anymore because you still have one more digit here. Okay, so how many options? 1, 2, 3, 4, 5. There are 5 options that I can use here. So now let's see. I had 10 numbers. I used 1, 2, so I have 8 left. There we go. Doesn't matter what this is as long as this is a 0 to a 5, not including 4. So 1 times 5 times 8, that's 40 ways. And then the addition principle of the fundamental counting principle says you can just add up the different cases. So there are 256 ways this can happen. And yay, we are so happy. We're 3/4 of the way through. Ooh, another one. This one is really, really similar. Yeah, I would recommend that you actually pause the video and try it yourself. So pause the video here, and then I'll very quickly go through the solution right after you unpause it. So, okay, you've unpaused the video. Here we are. The 3-digit numbers that are greater than 430. We're only using these digits here, so that's a little bit different. So, again, the easy mode here for me, I think, would be greater than 430 would be basically an 8 or a 9, right? Those are the only 2 numbers I could put here, so that would be 2 options. There's no repeats, so I had 1, 2, 3, 4, 5, 6. So there's 6 numbers. So I used 1, there's 5 left. And then I used another one, and there's 4 left. So multiplying these together, you get 40 ways. Okay, hard mode. Well, the hard mode would be obviously having a 4 here, right? Can't be anything else. So there's only one way for that to happen. And then you got to think about this digit. So it's got to be greater than 430. Now, I guess the big question is can you have a 3 here? So if there was a 3 here, what other numbers would I have left? So I've used the 4 and I've used the 3. A 1, 2, 8, or 9 in this position would make the number bigger than 430. So when I'm counting this, I really have 1, 2, 3, 4 options, right? 3 or higher. So I'm just going to write 3, 4, 8, or 9. So there's 4 options there. Oh, no, there isn't because I already used the 4. So my bad, my B. There's 3 options there. And then we had 6 numbers. We've used 2, so there'll be 4 left over. So 1 times 3 times 4, that's 12 ways. Fundamental counting, or the addition principle of the fundamental counting principle says you can add them up to get your final answer. So there's 52 ways to do this. All right. What if you have repetition? So, well, what does that even mean? Well, we're not stuck with just using numbers. We can talk about arrangements of letters. We can talk about arrangements of anything. In the future, we'll do arrangements of people, like not like a weird arrangement, but like people sitting in rows or in circles, stuff like that. So, say you got the word cat. How many different arrangements could you make? So we're not making words. We're just making arrangements of those 3 letters. Well, you got 3 letters, and we do not have to ask if repeats are allowed since we can only use each letter once because we're using these 3 letters, okay? So how many letters do you have on your first one to choose from? You got 3, and then you've used 1, and then you got 2 letters left, and then you've used 1, and you got 1 left. So there would be 6 arrangements. Well, okay. That's great. That makes sense. What about the word boo? So I'm going to make arrangements using the letters from the word boo. What's changed from the first question? Well, it's a different word, but also we have a repetition. We have 2 O's. So let's just take a look. Let's make the sample space for this one. Okay? Because we want different arrangements or unique arrangements of the word boo. So I'm going to start numbering my O's, okay? So we can just sort of distinguish between them. So we got the word boo with the first O and the second O. Now, if I'm making different arrangements, if you think of these as different objects, you could arrange it like that, okay? Now, this isn't chemistry. This isn't oxygen, although some of you guys probably need some oxygen, okay? But I'm just saying I rearrange these letters. Now, is this a different word? It's not, right? So that's not a unique arrangement. Okay, so I'll just circle and say that's not a unique arrangement. Well, how else can we arrange this thing? You can just cycle the B through. So I might go my first O, my B, and my second O. That's a new word. Just cycle the B through. So now the B's on the end. So I got oboe, oob. Is there anything else I can do? Geez. What about if I switch these two O's, right? If I go O2 and O1, is that a different arrangement? So even though we move the O's, this is not a new arrangement. Same thing with this one. I can switch the O's, but it's not a new arrangement. It's still oob, okay? So we got 1, 2, 3, 4. Are there any other ways we can do this? Oh, sorry. Right. This one's wrong. That's what made me confused. Okay, so when you go through, this is not a unique arrangement. So as far as unique arrangements go, you have 1, 2, 3. So there are 3 unique ways. Okay, so what's different? If you use the fundamental counting principle, you would have said 3 times 2 times 1, and there's 6 ways. And indeed, we found 6 ways, but because of the repetition, 3 of those ways are actually still the same arrangement. Okay, so how do we deal with this? Well, we use factorials. Okay, and it turns out that if you take the total number of letters or objects, so I'll just write letters, objects, because we do this with people as well, and you divide by the number of repetitions factorial, and same thing in the top. So if you take the factorial number of objects you have divided by the factorial number of repetitions, you will get the correct answer every time. So check it out. I have 3 letters, so I'm going to go 3 factorial divided by the number of repetitions. There was 2 letters that were repeating. Okay, 3 factorial is 6, 2 factorial is 2, and you get the 3 ways. So that is how we adjust our answer in the case of having a repetition. Easy enough concept, very tricky to understand always when to apply it. So yeah, we basically discovered there's going to be fewer different arrangements, and some of the arrangements will actually just be switching identical objects. So we use that factorial concept, but now we divide by the factorials of each repeating object to reduce the correct answer. Okay, so say just, we have this random question, you got n objects, but there's A identical and B identical and C identical objects that are within that n. So basically the formula is you take your total number, like I was saying, and you divide by each repetition, the number of each repetition factorial. So to demonstrate this, let's do how many unique arrangements of the word Mississippi are there. Okay, I chose this word obviously because there's a lot of freaking repetitions going on here. Okay, so first of all, figure out your n. How many total letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 letters. So the quick way of doing it is you're going to go 11 factorial divided by, okay, so we got 1m, so that's fine. But we got 1, 2, 3, there's 4 i's. So we're going to divide by 4 factorial because we got 4 i's, so we can sort of cross them off. We got 4 s's. 1, 2, 3, 4, and there's 2 p's. Okay, so this is for the i's, this is for the s's, and this is for the p's. Now, you would need your calculator, obviously. Maybe, I don't know. But you would go type it in on your calculator. I, for some reason, didn't. I didn't type it out on my calculator. So you'll just have to go type in 11 factorial, hit equals, and then divide by 4 factorial times 4 factorial times 2 factorial. I am certain you can do it. I don't even see my calculator. 4 factorial is 24. 4 factorial is 24 times 2. Okay, so there's an intermediate step. That's multiplication. All right. Sorry, guys. I don't have my calculator. My kid must have swiped it. All right. What about this question? So how many different 5-digit numbers can be made by arranging the digits, gosh darn it, of 17,171? Well, how many numbers are there in total? There's 5 numbers. So go 5 factorial. Now there's 1, 2, 3 ones, so divide by 3 factorial, and then there's 2 7s, divide by 2 factorial. This one should be a bit easier to do, because 5 factorial is 5 times 4 times 3 factorial. So we can divide out the 3's. 2 factorial is 2. 2 goes into 4 twice. You just have 5 times 2, so there's 10 ways. boys. You should be comfortable doing that, by the way. If they do give it to you on the non-calculated part of the exam, the answer would be such that you could reduce it in such a way. Now, they generally don't do that because that's sort of mixing concepts. Okay, but you never know, it could happen. Okay, we made it, you guys. Whew, that was a long lesson, but we really set up the entire unit. Everything from now on is just going to be sort of adding on to what we've learned. So you can go do exercise 8.1. And I put 2 additional supplements in the description of the video. I'll also throw them up on Teams, but boys, it's sure easy just to watch the video and then click on the subscription. So thanks for joining me, you guys. It was a blast. It was a slice. And we'll see you next time. Bye-bye.